Now in this video, let us see how we can calculate the age of a rock using uranium dating. And in this case, what is the intuition is basically to obtain that equation that can be used to calculate the age of a rock. So if I assume that n0 is the original number of it's the original number of uranium 238, and the rock that we have, the sample that we have, and this uranium 238, it decays, it will decay, and it decays according to the relation that we have, n equal to n0 e to the power of minus lambda t. Now this is the decay of uranium 238. So now this uranium, the end product of this uranium during its decay process is lead 206. So what will be the number of the lead nucleuses with mass number 206? That simply will be n0 minus n of uranium 238 nucleuses. That should be the case. So here we have n0 minus, this is n0 e to the power of minus lambda t. So n of lead 206 is going to be n0 times 1 minus e to the power of minus lambda t. So this is n of PB 206. So that's the case, okay? So if I choose this as, say, equation 2, and this is my equation 1, and I would like to divide the two, so dividing 1 and 2. Okay, I'm going to have a ratio. Okay, so the ratio will be what? It will be, that ratio I will define by R, and that will be n of uranium 238 by n of lead 206. So for this we have already n0 e to the power of minus lambda t divide by, for this we have 1 minus e to the power of minus lambda t. That's the case, right? And we will have R then. This R is giving us the ratio of uranium atoms and the lead atoms in a given sample. And here I must have N0. Yeah, N of lead 206 is N0 times 1 minus e to the power of minus. So N0 is here. This N0 and N0 will cancel. So I have a ratio, and I have e to the power of minus lambda t by 1 minus e to the power of minus lambda t. I would like to divide numerator by e to the power of minus lambda t. I'll get 1. So and denominator by e to the power of minus lambda t. Yeah, so here I will have e to the power of minus lambda t times 1 minus e to the power of minus lambda t. And here what we have done is we have divided numerator, and we have multiplied and divided by e to the power of lambda t. That will be the case. So if I multiply this with e to the power of plus lambda t, you will get 1 out of it. So R will be, so e to the power of lambda t will go inside. What I'll get is e to the power of lambda t minus 1. So this R is going to give me the ratio, and I can move on from here in terms of R. If I take it down here, so it will be R times e to the power of lambda t minus 1 is equal to 1. That should be the case, and then it should be like r e to the power of lambda t minus r is equal to 1. Okay, so r e to the power of lambda t will be r plus 1. So e to the power of lambda t will be 1 plus 1 by r. And what we will have log on both sides. And so having log on both sides will give me, it will give me lambda t is equal to log to the base e 1 plus 1 by r. So from this equation I have t, and this is 1 by lambda times log to the base of 1 plus 1 by r. So I can write down this distinguishing constant in terms of the half-life. So writing down it in terms of half-life will give me t half by 0.6931 log to the base of 1 by r plus 1. So using this equation, all I have to calculate is r, and I must know the half-life of the uranium. We will be in a position to calculate the age of the rock. It can be an age of a rock. It might contain uranium, or it can be any kind of monument in action. So simply using this formula, we can calculate, we can measure the age of a rock. Now, dear students, in this video, we would like to develop an equation by virtue of which we can calculate the age of fossils using carbon dating. And in this case, what we have is we have Earth, and we have Earth's atmosphere, and this Earth's atmosphere has it has high energy neutrons coming via cosmic rays, and they react with the nuclei of nitrogen. And when they react with the nuclei of nitrogen atoms to form a radioisotope of carbon C6 and 14. So how would we? So what we have is neutrons coming from cosmic rays from outer universe, hitting nitrogen, and creating the radioisotope of carbon and a proton. Now, all living things that we have, whether we have plants or animals, they have some quantity of radioactive C14. They have some quantity of C14. So as soon as a plant or an animal dies, this C14 it begins to decay, and it has a half-life. It has a half-life of 5,730 years. Now, since the half-life of this C14 is 5,730 years, therefore, if I take 1 gram sample of dead, say for example, dead wood or animal, showing an activity of 8, showing an activity we have calculated, activity, rate of distinguishing, showing an activity of 8. What does that mean? Activity of 8 distinguishations per minute. If it shows the activity of 8 distinguishations per minute, then it defines the age 5730 years. Now, if it shows 4 distinguishations, if the activity shows 4 distinguishations per minute, then it is 11,460 years old, and so on. So the point is, If we are able to calculate the activity of the sample, we can immediately talk about the age of the sample. We can predict how old the particular thing is, how old an animal is, or how old the plant is. So, so that could be the case. And now, if I assume here that I have R0, it is the activity. It is activity of piece of wood that we have been considering. Piece of wood. And and this activity, this wood has been obtained from freshly cut tree, and let R be the activity of a sample of burnt wood. Activity of burnt wood at some kind of archaeological site. Then we can write down this activity as R is equal to R naught e to the power of minus lambda t. And we can simply write out e to the power of lambda t is equal to R naught by R. And we can write down lambda t is log to the base of R naught by R. And we can calculate the time. That's 1 by lambda log to the base e R naught by R. So we can use for lambda equal to 0.6931 by t half. So t, the age of that fossil would be t half, say h by 0.6931 log to the base e r0 by r. So using this equation, this simple equation, we can calculate the age of a fossil buried under earth or found on the earth. That's it.